This episode of the Structural Engineering Channel is brought to you by Colliers Engineering and Design. Colliers Engineering and Design is a multidisciplinary engineering firm with over 1,800 employees in 63 offices nationwide and growing fast. Colliers Engineering and Design maintains an internal culture that is nurtured through the promotion of integrity, collaboration, and socialization. Their employees enjoy hybrid work environments, continuous career advancement, health and wellness offerings, and programs and projects that have a positive impact on society. Colliers Engineering and Design stays on the cutting edge of technology, and their entrepreneurial approach to expansion provides personal and professional development opportunities across the firm. Leadership's dedication to the well-being of their employees and their families is demonstrated throughout the wide range of benefits and programs available to them. For more information, visit the career page on their website at colliersengineering.com.
Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, we are talking to Michael Hopper, an associate partner at Lyra Consulting Structural Engineers, who is currently managing the School of Engineering and Applied Sciences and the Environmental Sciences academic complex at Princeton University. It's a series of hybrid timber, steel, and concrete structures that are organized to meet the performance requirements of these unique laboratory buildings while reducing embodied carbon. We'll be talking to him about the post-tension concrete structures, what they are, some of the advantages of using post-tensioning, and what he thinks about the future for post-tensioning. I'm your co-host, Matt Picardle.
And I'm your co-host, Kara Green. Now let's jump into our conversation of the week with Michael. Michael, welcome to the show. So to give our listeners a little bit of context about your background, can you please tell us a little bit about your career journey up to today, why you decided to become a structural engineer, and how you ended up focusing on the design of post-tension concrete structures?
Yeah, absolutely. Well, first of all, Kara, Matt, thank you so much for having me on your show and getting the opportunity to speak to your listeners. So how far back do you want to go? You want to go all the way back to
let's take it back to the beginning. Why did you choose structural engineering?
So structural engineering for me is something that I was always interested in architecture and building as a kid. And I was always good at math. So my parents encouraged me to go into architecture, but because I was good at math, they said, you want to be an architectural engineer. Without really understanding what that was or what that meant, so I kind of always had that in the back of my mind and was always pursuing that. But when it came time to pick a school, I chose Penn State because they have a fantastic architectural engineering program.
The Nittany Lions, right?
The Nittany Lions, yes,
from the
that's
Nittany
right.
Mountain Range.
Yes, of course, you know it. And so that's where my journey into structural engineering began. When we went to school at Penn State, it was, we had 4 different options. One was structural engineering. I loved it. It was exactly what I wanted to do. And I just sort of went after it. Interned at a couple of engineering firms locally, first outside of my hometown in Pennsylvania. And then 1 year I interned at Lyra in New York City. And when the opportunity came up to work at Lyra full time, after I graduated with my master's, I jumped on it. It was exactly what I wanted to do, and I loved it. So that's how I ended up at Lyra in New York. And so to answer the question about how did I choose PT, I don't know if I chose PT or it chose me. When I started at Lyra, the first project I worked on was a really unique post-tension concrete project. It was with Maki and Associates out of Tokyo, was the design architect. And the architect of record was Gensler. And it was for a project in northern New Jersey at a pharmaceutical company called Novartis. And when I joined the project team, it was really, really early in the design process. We didn't have a single drawing yet, but we had a series of sketches and ideas. And the architect wanted to pull back the perimeter columns from the building, and in order to open it up to the campus master plan. It was a community parks that these buildings were going to be built around. And our idea was to not only pull the columns back a little bit, but was to pull them back about 30 feet. So a real substantial move. And that move required post-tension concrete. And so there I was, a young engineer, just had graduated, working on my first PT project ever. And it happened to be a project with 30-foot cantilevers all around the edge of the building. And so it was a daunting task for me. And one of the first things I wanted to do is talk with other younger engineers about how they would tackle this problem. But unfortunately, we didn't really have any other younger engineers at the time in the office that had designed post-tension structures. The knowledge in the office at that time was mostly at the senior PM level. So for me, it was, man, I have to dive sort of head first into this post-tensioning pool, if you want to call it that. And it was just something that I ate up and I loved and I enjoyed. And that project turned out fantastic. It was a project that happened really fast, where I was designing a really unique long span cantilevered post-tension concrete building in a steel market. So not only did we have to figure out how we were going to design this, but it was also, we have to convince the owner that it was the right move, the contracting team that it was the right move. And the way that we did that was we brought in post-tension suppliers that validated our design and that this could be achieved. Just to give you a sense of scale, a normative post-tension concrete building has, I'm going to call it like 25 kips per foot of effective post-tensioning force. Our typical floor in this project had 3 times that. It was about 75 kips per foot. And our roof had 6 times that, about 150 kips per foot. So we're talking about a lot of post-tensioning in a market that's not used to building out of PT concrete at all. So it was quite a move, quite a bold move for that market and that time. And so the design was one thing. The other thing that the owner was really, really supportive of was having the right people on site. And so the design process took about a year for that project. The next year, I got to live full site, on site full time, seeing it all come together and working with the contractor and the trade. So I think that I got a really unique experience out of that. This 2 years from not a single drawing, just an idea or a sketch, to seeing the building open, right? It was just a really, really unique and great opportunity for me. So that's how I came into the design of PT structures.
It's a really cool story. I think it's I know Matt, and back when I was in design as well, it's always really exciting to go from the very, very base level of not even having drawings and just having a design concept all the way to ultimate like opening ceremony. So that's very exciting.
Yeah, for sure. And we try to get a lot of our younger engineers on site, but seeing a project from idea to completion is really remarkable, and it takes a long time for most of these projects. This one was unique in our experience at Lyra.
Yeah, and it seems like it wasn't a typical application to a 30-foot cantilever. You just try to envision that. It's a pretty huge.
Yeah.
It was,
when you said that, I was like, a 30-foot cantilever? That sounds like almost like an impossible problem from an exam or something.
Yeah, it's funny you say that. When the building was topped out, when they removed all of the shoring and reshoring, I was standing there with the architect from Maki & Associates, who was in from Japan, and he's laughing. He's much older than me. He's laughing like a little kid, and he's saying, if I would have proposed this in architecture school in Japan, I would have failed. They would have kicked me out. This should be impossible, right? So post-tension concrete is really remarkable, and it has a ton of applications, and it gives designers, structural engineers, and other designers a lot of flexibility, and we love it.
Yeah. Jumping into post-tension concrete or structures a little more, for our listeners that don't deal with post-tensioning on a daily basis, can you explain to them maybe what post-tensioning is, maybe in simpler terms, if they're just getting started?
Yeah, absolutely. And I think post-tensioning is one of those concepts that most young structural engineers coming out of school, or even while they're in school, it's a little misunderstood, maybe a little intimidating as well. So anytime I'm asked this question, I try to simplify it as much as possible. And the simplest response to that question that I've come up with is that we all know that concrete is fantastic in compression, right? And it's terrible in tension. So post-tensioning or any pre-stressing application is just pre-compressing that concrete so that when the structure is loaded later, the concrete remains in compression or has a minimal amount of tension. And that's really, really important because post-tensioning is a practical way. Right? I want to emphasize a practical way or a practical method that lets us use concrete in its most efficient way, which is in compression or with a little bit of tension. There's other technologies out there, right? Form finding structures, shell structures, arches, things like that, that you can really minimize, thin up concrete as much as possible. But that form has limited use, right? It's not practical for all of our building structures, but post-tensioning takes those same concepts of put the concrete in compression, how its best use is, and really leverage that and use it as much as we can.
I think that's the basis of it. It's concrete. If you've ever dealt with a mild steel before, mild slabs, for anyone that's designed those, yeah, that's one of the things. It's when you put steel in there, it's helpful, but once you get the post tensioning in there, you can remove, like even in if you think about post tension box girder bridges, the whole thing's essentially hollow, but then they put the post tension cables in there, and then you can really see what they can do with these long spans, because one of the weaknesses of concrete is that weight. And if you can remove a lot of that, replace it with post tension concrete, you can do really incredible things, like you were saying, with that cantilever and even with bridges. So it has a lot of applications.
Yeah,
yeah,
sure.
most definitely.
That crack control is really, really important, right? That takes a lot of I guess the unpredictable nature of concrete design or reinforced concrete design out of the equation. So it's much more reliable.
So you just mentioned that one of the key benefits is reducing the amount of concrete on a project utilizing post-tension. Are there any other key advantages that you can see when you utilize post-tensioning for concrete structures?
Yeah, there's certainly a ton of advantages. The main design advantage that I'd like to talk about is just that it's a volume reducing technology. So meaning that you can span longer distances than conventional reinforced concrete, or you can, for the same span, you can use a thinner slab or thinner beam. And that results in less material in your beams and your slabs. It also results in less materials in your columns, your walls, all the way down to your foundations, right? So that's a big advantage. When it comes to construction advantages, one major benefit is that you can strip your formwork much earlier with a post-tension concrete system than you can with a conventional reinforced concrete system, simply because as soon as you're stressing and those elongation records are approved by the engineer of record, you can strip your formwork. Some cities have other requirements and some jurisdictions do get involved, but in general, you can flip your formwork really fast. And that's important for concrete contractors to ultimately make money, right? They're out to make money.
Yes.
And that also, another construction advantage is that you have less congestion. There's less rebar in a project like that. So we find that in certain markets, you can build post-tension concrete structures super fast, really fast. Aside from those two sort of big advantages, I think the one thing that we at Lyra have really taken advantage of and leveraged is that post-tension concrete is really it's versatile, it's robust, it's often redundant, but really it's reliable. And it's reliable because we're controlling those tensile stresses. We're not seeing the same type of cracking that you get in reinforced concrete structures. So for a high performance building, we're able to reliably calculate deflections for post-tension concrete in a way that we can't do with steel, we can't do with reinforced concrete. And so for some of our projects where we have complex facade systems that have very, very tight deflection limits, we love to use post-tension concrete because we feel really, really good about it. And again, it's all due to the fact that we have uncracked section properties, and we're in that elastic range. We're not pushing into that inelastic range for concrete at those serviceability loads. And overall, it's a great performer.
Could you tell us a little bit about the history of post-tensioning, maybe some of the evolutions of post-tensioning? I know it came out in this century, I believe, if I recall correctly. How has it evolved in the past?
Yeah,
Know,
well,
10 plus
I'm
years?
I'm not that old, so I can't answer that. I can answer from my experiences. It came out, it came out by Freyssinet invented it, a French engineer back in, I want to say, I don't know if it was the late 1800s or early 1900s, but it didn't really catch on here in the US until I want to say the 1950s, where T.Y. Lin was a pioneer in simplifying it and using it in structures here in the US. I can speak to our project at Lyra and even the New York City market through my involvement with PTI. As a student, I know I had a bunch of misconceptions about what post-tension concrete structures could be. I had thought that they could only really be flat plate residential concrete structures where you're just trying to cram as many floors as possible into, said building. But in reality, there's a million different uses for post-tension concrete, and PTI is a great avenue for seeing some of those projects. There's the PTI awards that are handed out biannually, and there's always a unique application of post-tension concrete. There's several unique applications of post-tension concrete in those awards. But in the New York City market, I think it's been really, really interesting, and it's been game-changing for the post-tensioned industry. Post-tensioning in New York City had a bad rap for a while. And that had to do with a certain building in Midtown, and developers having a really, really difficult time going in and making modifications for tenant fit outs. We've done work in that building, so we know about those challenges. But there's been some advancements over the last 10 years, I think, that have made it easier for developers to implement post-tension concrete into their buildings. We've seen post-tension concrete be used in a banded tendon layout in New York City for a couple projects. One was one of our projects at Columbia University, the Vagelos Education Center, where we used banded tendons with void formers. That was back in 2014, 2015. And after that, there's a project at Hudson Yards where the structural engineer used banded tendons so that the developer, in that case, related companies, could punch out the middle of the bay down the road should a tenant want to come in and put in a communicating stair or open up the floor a bit. PTI is doing a lot of research right now. One of the research initiatives that PTI is doing is with Virginia Tech, and they're testing different tendon layouts, and one of them is a banded tendon layout. So just to back up, probably would be helpful to back up for your listeners who maybe are not familiar with post-tension design. In the United States, we are required, ACI requires structural engineers to, in at least one direction, have a maximum spacing between your tendons. So what's common to do is to band your tendons over columns in one direction, and in the other direction, you have a uniform spacing of tendons, which is limited to typically 60 inches. So that requirement has caused some limitations in how post-tension can be applied. The Post-Tensioning Institute, PTI, is doing some great research right now, and the results are promising. They're looking really, really positive. But within the next few years, you should see some changes come out to the code and open up these possibilities to other PT structures. But in general, we're already seeing it in New York. Now, there are ways to get around that. You have to design those slabs as just conventionally reinforced slabs. But we're seeing that happen. And as a result, on a lot of our developer projects in New York City particularly, we're getting asked to look at PT concrete, where in the past, it wasn't really an option. We're also seeing seismic applications of PT structures where we weren't seeing those in the past. We have a project.
I'm glad that you're touching on this. This was probably one of my main misconceptions around designing PT structures around seismic, because so when I first moved to Texas, there was conversations about, so our headquarters are in Plano and they're also in Oklahoma before we all made the big move to Plano. But they were talking about houses in Oklahoma were built with PT. It's like I guess the technical term is like a waffle foundation, where it has like PT cables run through the foundations of residential houses. But all of the slabs were cracking because there's some seismic activity in certain areas of Oklahoma, and they were causing the PT cables to loosen. So they were like losing their, I don't want to say it's
their pre-compression.
Yeah, exactly. So
okay. I don't know anything about that. That sounds really interesting, but I mean, I would think that that's a valid option anytime you have settlement issues in your foundations or expansive soils or anything like that. But yeah, that's interesting. But if we want to touch on seismic applications, there's been a lot of advancements over, I guess I'll say about the last 5 to 10 years. I'm sure you guys have seen some applications out west. Matt, you've probably seen these, right? You have rocking walls or post-tension concrete walls that basically self-center the wall after a seismic event so that the building is still habitable after a big earthquake. We've used post-tension concrete on a big project out in Los Angeles that we're doing right now. It's a base isolated building. But we're actually using post-tensioning in the isolation platform to make that isolation platform much thinner than if it were reinforced concrete. Both of those applications, we're still using the post-tensioning in its elastic range, though, right? We're not assuming that it's yielding. We're not using it for energy dissipation, and that's good because we know that post-tensioning 270 KSI strand is not. It's a pretty brittle material, right, compared to other steels. So I think there's still a lot of research that can be done on the subject, but I think engineers are cautious to use it where it's actually yielding.
Yeah, really interesting. Even some of the research with all the different structural systems that they're coming out with, like you were saying, the rocking walls. I've even seen some moment frame research projects where it's basically the structure goes back to where it was because of the post-tensioning, and it's really creative solutions for when other options might not be available. And
for sure.
So that was really interesting. Even the things that you said about the double banded tendons, that was a way to get more post penetrations for the owners if they need to penetrate the slab. That's an interesting one that I
That's right. That's right. In the New York City market, that's the name of the game, right? How can you design a structure that's flexible for tenant fit outs that are going to come down the road, and you don't know what those tenants are going to want. Some of them are going to want to interconnect floors, and steel has been used a long time in New York City because there's no building height limit either. So the increased structural depth is not a concern with steel versus PT. But you can modify it. You can with post-tensioning as well. It was always perceived to be more of a challenge, though, and this new structural system, this new layout, will open more doors for post-tensioning in urban markets for sure.
Yeah, and that's a great input. So I worked in Houston, and I know they had similar issues with retrofitting existing structures, and I'm sure that's a bigger issue in New York City, where square footage of non already constructed ground is a little bit more difficult. So you made the mention of the banded post-tension cables. How would you say that concrete technologies, because even though concrete has been around for forever, I feel like new research comes out all the time. How would you say that concrete technologies have made the construction industry more efficient?
Yeah, well, our efforts have really been focused in two areas, and I'll touch on those two areas. The first are technologies that really simplify the construction process. And the second is combining technologies so that we can harvest the benefit of each of those technologies however we need to solve a particular problem. And in concrete structures, about 50% of the cost is in the formwork. So that's a logical first place to start. And one technology that we love and that we found to be really, really beneficial in solving multiple challenges on a project are the use of void formers. Have you guys seen or heard about void formers?
I've personally never heard of it.
Yeah.
Yeah, I'll explain it. So they're basically recycled plastic balls, voids. Sometimes they're spherical, sometimes they're elliptical, sometimes they look like hockey pucks, big hockey pucks. Sometimes they look square with rounded edges. But the idea is that you're going to take these plastic voids and you're going to insert them in your concrete where you're not really relying on the concrete to do much for you structurally. And that does a couple of things. The first thing it does is it's going to reduce the volume of your concrete, right? So you're reducing the quantity. And you're saving all the weight that's associated with that. And that has the same benefits as post-tensioning in that your columns are going to thank you, your walls are going to thank you, your foundations are going to thank you because it has a ripple effect on the structure. But the thing that I think is most important that it does is that it simplifies your formwork. It allows you to build your formwork just as flat as possible, right? You can go out and build a flat slab where previously, in order to land to support heavier loads or span farther, you may have needed to use, say, a waffle slab or a beam and slab system or a joist system. So it really simplifies your formwork. So that's a technology that we're really, really happy with, that we've used multiple times, and it's sustainable as well. Another technology that we like to use is more of a mixing of technologies. And we wrote an article in Concrete International, the January 2022 issue. And our project was on the cover page. So maybe you guys can link to that in the show notes. And I'll also be presenting at the PTI convention in April, I think April 25th through 27th. In Southern California, just north of San Diego, where we're going to talk about this. And it's combining the technology of the void former that I just mentioned with post-tensioning. And I call it a PT slab on steroids because you're getting so many benefits from both of the systems, and they really complement each other really well. We span farther with less material using post-tensioning when it's combined with void formers. But the technical benefit, I don't know if you guys want to go into the technical area here, it changes the stress distribution. So by inserting a void into a post-tensioned element, the axial stress is going to increase more than your flexural stresses are going to increase. So we mentioned earlier that we're going to use post-tensioning to pre-compress that concrete, right? So you're going to pre-compress it by a factor of 2. And you are going to increase your flexural stresses by approximately 10%. So that increase in axial stress is going to more than overcompensate for the increase in your tensile stresses. And long story short, that's going to give structures or post-tension concrete structures the potential to span further while using less concrete and post-tensioning, which is really game-changing when you think about the environmental impact of that, and how can we minimize our carbon footprint, and how can we use less concrete. I think we have to get really creative in how we design post-tension or any concrete structure moving forward. And that's one that we're really, really excited about.
No, that's great. And so you mentioned these void formers, and just for my understanding, so I have seen structural styrofoam put into specifically stairwells. Is it something like because I'm a picture type person. I think a lot of engineers are. When I think of it in that way, you said that the void formers don't necessarily provide any structural integrity to the structure. The concrete, this is an area where the concrete is not underutilized for its full strength. So is it different than, say, a structural styrofoam?
Oh, it's the same. I mean, it's the same concept, right? If you're using styrofoam and stairs, likely it's a stay in place form, right? Mm-hmm. But it needs to have some rigidity to it so that it just doesn't collapse under the weight of the concrete. So it's the same concept, and it could be out of anything. It could be used. You could use styrofoam as your void former, but the companies that are manufacturing these are really smart, and they're using recycled plastics, and they're actually shipping them in a way that they stack up like a bunch of cereal bowls. So they're basically these half circles that then sit like cups on a truck, and then when we get to the site, they just flip them over and click them together like that. And so it's a little more sophisticated than that, but it theoretically, from a structural perspective, how we rely upon the void to function within the concrete section, it could be anything.
Yeah, it's basically, if I'm picturing it correctly, I might have seen some pictures in a book before. It's basically like those plastic balls that are hollow. You stick them in the slab where basically the concrete's not doing much, so it's just added weight. So you replace that added weight of concrete, replace it with a hollow ball, and now you don't have to balance all that heavy concrete. And like you were saying, combine that with post tensioning, yeah, you don't have to balance as much concrete. So that's definitely a interesting application to see where that goes.
Yeah, no, it's really exciting, and we've used it on a few projects, and they've turned out great. But I think that's a technology that if we're gonna get serious about reducing the carbon footprint of our concrete structures, that's one that we all need to take a hard look at.
So I know you've mentioned reducing the carbon footprint. So I'm guessing that post-tensioning is significantly environmentally sustainable rather than just regular reinforced concrete. Obviously, and there's the 2050 environmental commitment report or commitment challenge that's going on right now with, I think it's ASCE or NCSEA. And then, so what would you say as someone who is working in the concrete industry? You have this experience specifically with PT, and you're very knowledgeable around the sustainability factor of post-tensioning and reducing the carbon footprint of concrete, because it is a very high carbon construction material. What do you see as the future for post-tensioning concrete, especially around sustainability?
Yeah, it's a really good question. Well, first of all, I think that post-tension concrete is absolutely environmentally sustainable, and I think there's 3 points that I want to highlight. The first is the one I mentioned earlier, that it's a volume reducing technology, and therefore PT structures use less concrete than and therefore have less embodied carbon than other concrete structures. So that's really, really important. Number 2 is that if you talk about sort of total building volume, if you want, let's take a step back and look at sort of some statistics about carbon in general. About 10% of global CO2 emissions each year are due to embodied carbon in our construction projects. Okay. But about 30% of that, or about 30% of total global CO2 emissions are due to the operations of our building, right? So you have to think about total building volume and what it means to heat and cool and use more space. And one thing that post-tension concrete has going for itself over other structural systems is that the structural depth is significantly less. Right? I've seen post-tension concrete floors down to 6 or 6.5 inches. You can't do that in other structural systems without throwing in a million columns at it, right? So I think post-tension concrete has that. And the third point is really about longevity. Post-tension concrete is a very durable system. It's resilient and it's adaptable, and it's really attractive from a long-term standpoint, where you're trying to reuse structures rather than building new. So I think that those are 3 really important points that post-tensioning hits on well, and it's one that I see those as a benefit over other structural systems, be it steel, be it mass timber, or whatever. The future of PT concrete is another good question. I think it's likely going to include some type of hybrid structure, whether that's concrete mixed with mass timber, mixed and matched with structural steel. We have a few projects in our office right now they're approaching the challenges on those jobs that way, where we're using concrete to its best use, and that happens to be underground on that project. We're using mass timber in office spaces and public spaces because it's beautiful. People want to see it. And then we're using structural steel, where we have very, very strict performance criteria, all in the same building. So that's one potential way that we could tackle this challenge moving forward. But the other is just, if we're just going to talk about concrete, is just mixing technologies within concrete. I think the concrete industry is uniquely suited in that it's easy. It's really, really easy to mix high strength rebar, post tensioning, void formers, carbon reducing admixtures, things like that, into your structure. Or it's harder to do that when you're mixing steel and timber together and all these other technologies. So I would guess, if I had a crystal ball, that we would start to see emerging technologies inside of concrete, cast into concrete, and more hybrid structures.
Thanks for that, Michael. To end off here, did you have any final piece of advice for engineers considering a career similar to yours?
Sure. I don't know if it's an engineer or if it's a career similar to mine. I think it applies sort of broadly to structural engineering in general. And it's going to sound a little cliche, but I think it's really, really important for engineers to follow their passions, right? I think back to anything that I've done particularly well, it's something that I've been really, really passionate about, whether that's in, life in general, or in sports, or in school, or in structural engineering. So for me, that just so happened to be that I really loved and enjoyed post-tension concrete, and that love, that passion for you through the hurdles, right? That's what keeps you going. So that would be my advice. Another piece of advice that I always give to other engineers is just to focus on helping solve other people's problems, right? I look back at other structural engineers, look back at other great structural engineers, and reading their writing, seeing them speak, really old structural engineers, seeing their recordings on YouTube, and none of them are talking about engineering challenges, right? They're talking about, how do I solve an architectural challenge, an issue with society, an owner's challenge, right? These are the really, really successful structural engineers are not just focused on engineering problems. They're thinking more holistically. So I think that's another one that's really important that I try to keep in the back of my mind when I'm working on a project, working with a client or an architect, is trying to listen and understand what the real issues are and how I can design a structural solution that tries to solve all of them and is still the most efficient structurally. So,
yeah, great advice. I love that we're problem solvers, but using our profession and using this art of structural engineering, we can help not only just basically using our art to help solve that bigger picture, like you were saying with the architects, or even this sustainability issue that we're trying to get more of. We can dive more into that, which you obviously are. But I think as a whole, we can, if we're really passionate about it, you can dig into it. And like you were saying, it'll definitely get you through the tough times if you're doing something that you love.
Yeah, for sure. But I think the sustainability issues strongly need structural engineers to get involved. So props to SE 2050 and everything that the ASCE and the Structural Engineering Institute are doing, because I think that whole conversation needs structural engineers.
Yeah, and it's a very popular topic right now, especially with everyone becoming carbon neutral. There's a lot of large firms that are really working to provide that sustainability piece. And it's nice to see, I guess, almost the community come to help solve the problem, I guess is the best way to put it, because it seems everyone is aware of the issues and is really doing their best, either inside their firms or personally in their own design methodology when they're sitting at their desk to provide sustainable solutions. It's going to be a fun problem to solve. You get to be creative a little bit in how we move forward.
Yeah, that's well said, Kara. And it's another design constraint for us as structural engineers, right? We have many to begin with. This is just another one that we can use to hopefully come up with most efficient structure.
Yeah. Well, thank you so much for your time, Michael. We appreciate having you on. It was great to hear your perspective and a little bit more about post-tensioning. You blew my mind a little bit about a few preconceptions I had.
Well, that's great, Kara. I'm glad to hear that. And thank you both. Thanks, Matt. Thanks, Kara, for having me on.
Absolutely. Thanks, Michael.
I hope you enjoyed the episode today with Michael. We would love to hear your feedback, comments, and or any questions you may have. To leave them, please visit structuralengineeringchannel.com. There you will find a summary of the key points discussed in today's episode, which is episode number 73, as well as any links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all your structural engineering endeavors.